Okay, so the first thing I need to cover is it's called growth of functions. This is our lesson 4.3, growth of functions. Okay, growth of functions, and I often just abbreviate functions. I'll just abbreviate functions by just saying f of x. That's pretty much saying the same thing. It's just shorthand for saying functions. I just want to talk about growth of functions real quickly because we talked about linear functions yesterday. I'm just going to review that real quickly. We talked about linear functions yesterday, and so if I had an xy plane, a Cartesian coordinate system, if you will, and if I had two lines, I had a green line like that, and I had a blue line like so. Which line has the greatest rate of growth? Blue, yeah. So this one has the greatest rate of growth. It has the steeper slope. It's raising faster. Now here's something of interest that I want you guys to be aware of. It has the greater rate of growth, but when you look at it here, you can see that the green line is above the blue line at that point. So if this were like a negative, negative n, doesn't matter what number it is, the green line is above the blue line. So a misconception might be, if you only look at that little tiny sliver, you might think, oh, the green line is of a higher value than the blue line, therefore it has a greater rate of growth. But that would be incorrect. We have to kind of zoom out and look at the entire system to see that the blue line is in fact growing higher or growing faster than the green line. Does that pretty much make sense? Thumbs up if that's pretty clear. Thumbs down if you want me to go over that again. Okay. It's kind of intuitive, but I can see it being tricky, so I kind of wanted to slow down and look at it. Make sure everyone has their notes up. Okay, so what I want to do is, these are linear equations, but we don't always work with linear equations. Sometimes we work with exponential functions, right? Exponential. This might be something like a geometric growth. Okay? So if I had something like f of x equals, 2 to the x, something like that, let's look at what happens with this function. And I'll build just a basic t-chart to understand it. Okay, so when x is 0, 2 to the 0 is 1. Excuse me. When x is 1, 2 to the first is 2. When x is 2, 2 squared is 4. When x is 3, 2 to the third power is 8. Makes sense, right? And we have that exponential growth, 1 to 2 to 4 to 8. We're doubling each time. But what about if I go backwards? What if I go to negative 1? Okay? If I go to negative 1 for my 2 to the negative first power, what does that become? Okay? Clear. So we can do this with our calculators if we don't know it off the top of our head. I'll do 2 to the negative 1 power. Does anyone want to take a guess of what that becomes? 1/2, absolutely. And we'll see that. 1/2. 1/2. And so we go to the negative 2 power. 2 to the negative 2 power. 2 to the negative 2. And what does that become? Anyone want to give it a shot? Quarter. 1/4. Brilliant. So on and so forth, right? But what we see here is these, as we go negative, the number gets smaller. It gets so much smaller. So on my graph, I'm gonna do this because I want to talk about this growth. Okay. So when I'm looking at this exponential function, I look at negative 2 and I see that it's a quarter. Well, that's like very close to the line, right? A quarter? It's like right there. When I go to negative 1, it's a half, which is, halfway there. 0 is 1. 1 is 2. 2 is 4. 1, 2, 3, 4. And then 3 is 8, which I don't even have written down. It's like all the way up here. All right? So let's look at the behavior of this line, right? Let's look at the behavior of this line. So what is it doing? It's doing something like this, where it's like, as I go positive, as I go positive here, what do we expect the line to do? Right? When I go from -2 to -1, it's kind of flat, right? I'm going to do it in pencil. We see as I go from -2 to -1, it kind of does something like that. You can faintly see the pencil of that growth. But that's the linear growth, and it's not behaving linearly. In fact, it goes up even more to right here. So if I were to connect there, from -1 to 0, I see that my line, well, it's increasing still. And then from here to here, it's increasing even more. And so on and so forth. Right? Each time, it gets steeper and steeper as I increase, right? So the rate just continues to rise like that. But as I go backwards, it's going to get smaller and smaller and smaller until it essentially looks like a flat line. So here's the trick. The rate of growth of this blue line is kind of tricky because it all depends on how we look at it. If we only looked at, if we ignored everything and we only looked at this little tiny sliver right here, it looks like there is no to minimal growth happening in this function, in that blue function there, right? Because it looks flat. But we have to zoom out and view the big picture. When we view it here, we see that there's an insane amount of growth, an exponential amount of growth. It's doubling, in fact. And that's a very impressive, very large amount of growth. So if I were to look at something like this and compare it to, say, a linear equation. If I were to compare it to a linear equation. Let's say I had a line that went like this. And I asked you, what had the greater rate of growth? The blue line or the green line? Alessandro? Yeah, the blue is going to keep doubling and doubling. Now there's this weird period right here, and this is just like I was saying with our linear equation, right here where the green line is higher than the blue line. And in fact, there's definitely a significant portion where the green line has a steeper slope than the blue line. But again, we have to zoom out, look at the big picture, and see that the blue line is racing towards infinity much faster than the green line is. Yeah?
In theory, won't any exponential function, so long as it's positive, have a greater rate of change than any linear function, even if it's like 300 up?
Yes, the only difference would be a very vertical line. So what Essence was asking is, in theory, wouldn't any exponential function have a greater rate of change than a linear function? And the answer is yes. The only, and it's not actually a function. If a vertical line, I guess, is technically growing faster. But even if it's just a hair, the tiniest hair, even still an exponential function is going to be growing faster. Because on a long enough time frame, double, double, double for infinity, eventually it's growing faster. Absolutely. Now we will get into situations where maybe you will have two exponential functions, and we have to figure out whether or not one exponential function grows faster than another. But again, looking to see which one has the greater rate is going to help you. Because remember, this is going to translate into the next part I want to talk about, which is reviewing explicit for geometric. Remember, when we're talking about exponential functions, we have another word for that we've been using, and it's geometric. Right? And remember, the base form of a geometric explicit equation will be f of x equals our first term, whatever our first term is. So I'll say n to the 1 power. It's our first term times our rate to the x minus 1 power. Okay, that's our base formula for that. And we can find our rate very easily. It's that number that is being raised to the power. Okay? It's that number that's being raised to the power here. So for this one, this guy right here, I'll just scoot this down a little bit. We can see, well, where's the n1? Well, we know there's an invisible 1 right here. So we know that our first term is 1, and sure enough, that's true. But 2 to the x, well, that's our rate, right? So if I had f of x equals 2 to the x, and I had f of x equals 4 times 3 to the x minus 1, if I had something like that, and I asked you which of these had the greatest rate of change, which one grew faster, which one approached infinity at a faster rate, would it be equation A or equation B? It'd be equation B. Hallie, why did he say B? There's a very obvious clue as to why this, I know you know, that's why he told me. But there's a very obvious clue to why B is growing faster than A. We don't have to graph it to know it. We can look at it and see it. David? Which number specifically? Because it matters which number we're talking about. Tessa? 3 is bigger than 2. Remember, this is our rate right there. Our rate is the number that has the exponent being raised to it. So the fact that 3 is a larger number than 2 tells me that B is going to increase at a greater rate than A. Even with the multiplying by 4, it doesn't matter. Because that's just going to be our first value, right? It doesn't matter what our first value is when we're talking about rate. Okay? Because this could be something like this. Here, I'm going to draw another little chart here. So we could have a Cartesian plane that looks like this. Cool. And we could have one function that has a very high starting value. Maybe it goes something like this. Okay? And then we could have another function that has a lower value, but goes like this. So which has the fastest rate? It's the red. Okay? The red is going to have that faster rate of change. Yeah? Maybe. I'll think about it. Okay? So this is all the good stuff that you guys need to know to be able to do this next section. Any questions? Thumbs up, we're feeling good. Thumbs sideways, need a little refresher. Thumbs down. Victor, why are you doing this to me? All right, cool. So I'm gonna pause this thing. I'm gonna give you guys time to work on stuff, ask questions. I'm happy